Hey, this is chapter 4, the example problems from Young and Friedman's University Physics 14th edition. This is chapter 14, chapter 14.1. Example says period frequency and angular frequency is the title of this problem. It says an ultrasonic transducer used for medical diagnosis oscillates at 6.7 megahertz. So 6.7 M, that's M. I know it looks like an H, but that's an M. Megahertz. All right, which is 6.7 times 10 to the 6 hertz. And how long does each oscillation take? And what is the angular frequency? So we want to know T, period, and omega. So first of all, T equals 1 over the frequency. So we've got 1 over 6.7 times 10 to the 6 hertz. And that's going to give us 0.15 microseconds, 0.15 microseconds, which is 0.15 times 10 to the negative 6 seconds. Okay, that is the first one. And now to find out omega, the angular frequency is equal to 2 pi f. I think it's raining outside. Is 2 times pi times the frequency was 6.7 times 10 to the 6 hertz. And we're going to get a value of 4.2 times 10 to the 7 radians per second. And that's 14.1. Example 14.2 says, angular frequency, and period in SHM. SHM is simple harmonic motion. All right. A spring is mounted horizontally with its left end fixed. A spring balance attached to the free end. A spring balance attached to the free end and pulled towards the right indicates that the stretching force is proportional to the displacement. And a force of 6 newtons causes a displacement of 0.030 meters. So let's jot that down, 6.0 newtons. That and delta x is 0.030 meters. We replace the spring balance with a 0.50 kilogram glider. So mass glider equals 0.50 kg. Pulling it 0.020 meters to the right. So this is delta x1 and delta x2 equals 0.020 meters. Along a frictionless air track and release it from rest. Find the force constant K of the spring. That's A. Find the angular frequency omega, frequency F, and period T of the resulting oscillation. Okay, A. From Hooke's law, we know F equals Kx, where F is the force, K is the spring constant, and X is the displacement from the equilibrium position. So 6.0 newtons divided by 0.030 meters equals K. K is going to equal to 200 newtons per meter. Or you can rewrite that as 200 kg per second squared. I don't know why they did that here, but I'll show you how that works. A newton is a kilogram meter per second squared divided by a meter is simply going to be a kilogram per second squared. I don't really know why they went there. Maybe it's going to help with the rest of the problem. All right, that's 14.2a. In part B, we are supposed to solve for the angular frequency omega. That's going to equal to the square root of K over M. More M and omega is slower, more K and omega is faster. That makes sense. The stiffer spring is going to give the faster angular frequency, and more mass applied to it is going to slow it down. All right. So we've got 200 kilograms. This is why they did that, per second squared over, and they applied that card of 0.50 kilograms, and omega is going to be 20 radians per second. Okay, so now C says find the frequency F. Okay, F, oh, C. Sorry, F, 2 pi F equals omega. So omega is going to equal to, I'm sorry, F is going to equal to omega over 2 pi, which equals to 20 radians per second divided by 2 times pi. And that's going to be 3.2 hertz. So F is going to be 3.2 hertz. That's 3.2 cycles per second. Finally, find the period, which is called T, and it's simply 1 over F. So it's 1 over 3.2 hertz. So that's going to be equal to 0.31 seconds. That's T. And that was 14.2. This is example 14.3, which reads, it's called describing SHM, which is simple harmonic motion. And we read, we give the glider in example 14.2, an initial displacement x naught equals plus 0.015 meters. And an initial velocity, v naught sub x equals plus 0.40 meters per second. Find the period, amplitude, and phase angle of the resulting motion. Write equations for displacement, velocity, and acceleration as a function of time. All right, so from 14.2, we know the angular velocity was equal to 20 radians per second. And we know the period was equal to 0.31 seconds. All right. Okay, so A, find the period. A equals, this is from equation for the amplitude. We're finding the amplitude right now. Find the period. Okay, so we already know the period from example 14. So now I find the amplitude in this equation 1419. So the amplitude equals the square root of x naught squared plus v naught x squared divided by omega squared. So this is going to be equal to A equals square root of 0.015 meters quantity squared plus 0.40 meters divided by 20 radians per second. And that's all squared, the whole thing. So we're going to get A, I'll put it over here, A equals 0.025 meters. To solve for the phase angle phi, we are going to use equation 1418. So phi equals arctan of negative v naught x divided by this is going to be omega times x naught. So this is going to be arctan of 0.40 meters per second. Negative, this is all negative, divided by 20 radians per second times 0.015 meters. That's going to equal to negative 53 degrees. So E equals negative 53 degrees, or negative 0.93 radians. Okay, now to write equations for the displacement, velocity, and acceleration. We're going to use equations 14, 13, 14, 15, and 14, 16. We have x equals 0.025 meters times cos of 20 radians per second t minus 0.93 radians. And v sub x is going to equal negative 0.50 meters per second times sine of 20 radians per second t minus 20 radians per second times t minus 0.93 radians. And finally, our acceleration a sub x is going to be equal to negative 10 meters per second squared times cos 20 radians per second t minus 0.93 radians. It was 14.3. Example 14.4. We're still using that example from 14.2. Hey, find the maximum and minimum velocity displayed by the oscillating glider. That's my phone, if you'll pardon me. This is example 14.4. It's velocity, acceleration, and energy in SHM, simple harmonic motion. And it reads, find the maximum and minimum velocities attained by the oscillating glider, example 14.2. Find the maximum and minimum accelerations. Find the velocity and acceleration when the glider is halfway from its initial position to the equilibrium positions, x equals 0. Find the total energy, potential energy, and kinetic energy at this position. Okay, we're going to go ahead and use equation 14.22 to find the velocity at any displacement. So v sub x equals plus or minus the square root of k divided by m times the square root of the amplitude squared minus that position from the equilibrium distance squared. All right, and now the maximum speed occurs when the glider is at x equals 0, or at that equilibrium position. So V max equals square root of k over m times a. And that's going to be equal to square root of 200 newtons per meter divided by 0.50 kilograms times 0.020 meters. And Vmax is going to be 0.40 meters per second. All right, so the maximum and minimum velocities are 0.40 meters per second and negative 0.40 meters per second. And it occurs through x equals 0 when the cart is moving from the right to the left. All right. The gliders, okay, so now for part B. Glider's maximum acceleration occurs at the most negative value of x. That is x negative a. Our equation here is a sub x equals negative k over m times x. That's where that is going to be a maximum or minimum. So we have a max equals negative 200 newtons per meter divided by 0.50 kilograms times a negative 0.020 meters. That's going to be equal to 8 meters per second squared. And the minimum is when A is positive. So that's going to be just simply 0.020 meters. And we're going to get, that's the only difference. This all remains the same. It's going to be equal to negative 8 meters per second squared. All right, the halfway point from x to x naught is going to be equal to a over 2. So equals 0.010 meter. So we have v sub x, the halfway point, equals the square root of 200 newtons per meter divided by 0.50 kgs times the square root of 0.020 meters squared minus 0.010 meter squared. And for this answer, we're going to get equals negative 0.35 meters per second. And it's negative because the glider's moving from x equals a towards x equals 0 inward. Okay, for a sub x, it's going to be negative 200 newtons per meter divided by 0.050 kilograms times, we'll use that value, 0.010 meters. And we're going to get equals to negative 4.0 meters per second squared. All right, now we are to find the total energy, potential energy, and kinetic energy at this position. Total energy is equal to E equals 1/2 K A squared. And that's going to be 1/2 times 200 newtons per meter times 0.020 meters, quantity squared. That's going to be 0.040 joules. All right, and the potential energy, U, equals 1/2 kx squared. And that was the midway point, so we've got 1/2 times 200 newtons per meter times a 0.010 meters, quantity squared, and that's a 0.010 joules. And finally, our kinetic energy, K, equals 1/2 mv squared. Mv squared, we've got 1/2 times 0.50 kgs times negative 0.35 meters per second, quantity squared. That's going to be 0.030 joules. And if you note that these two add up to this guy. And that was 14.4.